Okay, hi guys. This is a single phase inverter. Inverter means we will invert, we will go back from DC into AC. Okay, let's see here. But before we start, let's look at the different transistors that we have. In electronics, you studied which transistor, guys? Huh? This one, BJT, right? Bipolar junction transistor. And in the power electronics, in buck and boost, we studied Mosfet, right?
Yes.
And then IGBT. What's the difference between those three? I mean, which one to use? Want to use this one right here, want to use this one, want to use this one. Let's say you have a project, say you have a mini project. Which one you will use from those? Which one do you use? Mosfet or IGBT or BJT? It depends. Okay, you need to know the good thing about this and the good thing about this and the good thing about this one right here. Bipolar junction transistor. It works, remember guys, the three legs, base, emitter and collector and emitter, right? Base, B, C, and E, right? Those are the three legs. And the base depends on what? Voltage or current? The base. We give the base current, right? So if there is more current, enough current, then the current will pass from the collector to the emitter, right? And the voltage, if you still remember the voltage between collector and emitter, is it small or big? It's big. So we can say here that BJT, it has high voltage and low current. Okay? So actually it depends on the current. The more current you give, the more current it flows from the collector to the emitter. That's the BJT. Okay? So if you're looking for high voltage but you have only small current, you can work with small current, this is a good choice. Let's look at Mosfet, which we used in choppers, buck and boost. What's the good thing about this? Fast, okay? This is fast. It depends on voltage. So it works with voltage. The gate, it has gate. You know, what are the three legs? Gate and what? Drain and source, right? Drain and source. So you have a gate and then you have a drain and source. It works with voltage from the drain, from the gate, sorry, but then the voltage between the drain and source is small. And we have one of the groups, they apply high voltage in boost. They apply 120 volts and the duty cycle was high and one of the transistors was burned because it cannot handle it. I mean the range for Mosfet is less than 1000 volt. So if you apply, imagine in boost, what's the equation for boost? V out.
1 minus.
V source 1 minus duty cycle, right? So if the duty cycle is 95, then and the source is 120, 120 divided by 0.05, how much? It's over 2000, right? So that's huge volt, and this will be burned. So here, when it comes to IGBT, do you guys see any relationship between IGBT and those two right here? IGBT. What's BT? BT is from here, which is bipolar transistor. But the gate is from here. So it took the best good things from both. So this one works with high voltage and high current. Fast, it's fast, and it can handle a huge amount of voltage. That's why we will be using this one in inverter, because we will have high voltage actually, and also we need high switching on off a lot. So we're looking for fast transistor, at the same time something that can handle. Can we use Mosfet today?
No.
Yes, we can. We can, but we have to be careful about the voltages. We have to work with small voltage. Okay? But this one is better, this is more safe. Which one, if you have a mini project you will use? Which one?
Mini.
It depends. If you have a project, which one you will use? It depends. If your project doesn't need high current and it needs high voltage, use this, because this is cheap, guys. This is the cheapest. This is medium. This is very expensive. But if your project needs a high voltage and high switching, this is the one. Yeah, it's expensive. Use this. Okay, but mostly Mosfet we use it a lot because it's, you know, the price is okay. This is IGBT, guys. This is IGBT. And this is the gate, and this is the, you can look at it like this. This is IGBT right here. I think this looks close to the Mosfet. Okay, let me fix this one right here. Okay, so here, and then I have this one right here. Okay, and this is the gate. Okay. Okay, this is IGBT. Let's look at this circuit. What's the source?
DC.
The source is DC.
DC.
So the current will, we have to play with the switches, guys. We'll close switch 1 and switch 4 for 50%, and then what we will do. So close this and this. Look at it as switch, guys. Look at this as switch. As a switch, guys. Switch. Look at it as switch. For the time being, look at it as switch. So I will close this switch and I will close this switch. So I will close 1 and 4. So what will happen? The current will flow, right? It will flow through the diode, right? No. It will not through the diode. It will flow through the transistor, right? Through the IGBT. So it will flow through the IGBT. Then through the load, right? Because this is open. Then through the load here. Then through the IGBT here. And then it will come back. Okay? Clear?
Yes.
Then what should I do after this step?
Close 2 and 3.
Close 2 and 3. If I close 2 and 3, there's an issue, guys. I will have a short circuit. So I cannot do this.
Open 1 and 4.
I have to open 1 and 4.
Then?
Okay? So the process, if you look at it, then close 1 and 2, right? Then open 1 and 2. You have to open them. Then close 3 and 4, and then open 3 and 4. So if I ask you what would be the steps to avoid a short circuit, you have to give me those steps.
Teacher, you mean 1 and
4.
Sorry, guys.
3, 2.
1 and 4, and then 1 and 4,
3, 2.
and then 2 and 3, huh?
Yeah.
It's your fault, guys. You should tell me before I write. I'm using green, guys. Okay, so let's see here. Now, I will open 1 and 4, and then I will close 2 and 3, right?
Yes.
So the current, I'm going to use red, guys. Now this is close, and this is close, so the current will pass, not through the diode, through the current, through the transistor, guys. Okay, and then look at the direction, guys. The direction before was this way, right?
Yes.
Yeah, so that's what we have done. And now the direction right here through the
Opposite direction.
IGBT, opposite direction. That's what we have done. We create opposite direction. Let's come here.
Teacher,
Yes.
this is same like the bridge controller and control rectifier.
Uh,
Same idea.
No, this is we create two different polarities, right? We create positive and negative, right? Here, we create positive and negative. Let's see here. That's what we have created. Positive, negative, positive.
Yes.
Is this AC? So this is so what we have done. We invert DC into AC. This is a square wave. Is it good?
No.
No, we don't like this square wave because we will have also issue with the current. Let's look at the current. Let's see what will happen with the current. The current, what will happen here, guys? What will happen for the current? The current will pass through here, right? And it will go through the inductor. What will happen in the inductor? Charge, right? It will increase. And then, what will happen? Because actually I will close, it will increase, right? Then when I open, what will happen?
Discharging.
It will discharge. But where? Pay attention to this point, guys. You guys see this? The green. Okay, charging, right? I open 1 and 4. I open 1 and 4. But I still have, no, it's not discharging yet. But I have something stored right here. This will work as a source. What will happen now?
The focus diode.
Yeah, which diode, guys?
1 and
No, the 3 and 4.
Yes.
It will continue discharging. So since you open this and this will work as a source. So it will, the current which was stored, it will go through this. And then through this diode right here, and then back till it releases. Okay? This way. Okay? Is that okay, guys? Same thing with the red one. Then after that, I will close what? 2 and 3, right?
Yes.
When it close to 3, the red one here, it will go through the IGBT, then here. Then after that, when I open 2 and 3, now this will discharge, right? It has to discharge through 1 and 4, right? So it will go like this. Through the power diode, right? Through the power diode, and now through this diode right here, right? Right? Is that okay? Yeah, that's why I intend to record it, so you can go back and, because sometimes you guys forget. Regarding the DC, we explained the DC, we said it's direct current, means it goes from positive to negative. And then the AC alternating current and polarity changes. This is the key here for AC. Polarity changes per cycle means it will be positive and negative 120 times per cycle, 60 times positive and 60 times negative. And I gave you example regarding the DC live example, which one? This one is like river, it goes one way, and the AC like tide, right? Goes back and forth. So that the direct current goes from positive to negative or the opposite. But alternating goes back, front, forward and reverse, and so on. Let's look at this. Let's assume that we only have this cycle. Okay, what will be the shape of the current? The shape of the current will look like this: charging, right? I should not go all the way all the top. Charging, and then discharging like this. Charging, and then discharging. You guys like this? This current, is that okay? Oh, we have huge harmonics right here, bad. Yeah, we will have, this will create heat, losses, and humming. Okay, we have a lot of harmonics. So we're not satisfied with this. So how to solve the issue of this current, what to do? We have inductive here. We're gonna use huge inductive at the end, but before huge inductive, we need to solve this issue using pulse width modulation. So we're gonna use pulse width modulation, right? Pulse width, that's a technique. How to use that? Okay, let's look at this, how we will divide this. Okay, I'm gonna use, let me use the green. Okay, we will divide here like 7. So the middle one will be the biggest on, and next one will be, next ones to it will be the same size, less, less. Okay? And the next one will be smaller. Okay? Next one will be smaller. So the way, this is the peak, right? At the peak, you will have the biggest pulse, which is the biggest on, the biggest duty cycle. And then after that, it will be smaller, smaller, and smaller. So the next, okay? See here, smaller. And then here, smaller, okay? And then you can go smaller. And then you can go smaller, okay? So I think I have 9. This is 1, 2, 3, 4, 5, 6, 7, 8. Actually, this is 1. I have this is 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm not that good in drawing. I mean, comparing to the pulse width modulation technique, I'm a little bit better, guys. Okay. So when you compare me to there, you will see that there's some mistakes in the pulse width modulation, but with my drawing, you cannot see no mistakes, okay? We'll do the same thing right here, guys, okay? So it's the opposite, so I'm gonna come to the middle right here. I'm gonna have the biggest, right? Which is the peak. And then same thing, I'm gonna go with the bigger one. I'm gonna go with bigger one, guys. Okay, then I will go with a little bit less. I think I make it too much less. Then I have this one here. I know you guys like this noise. Okay, so then 1, 2, 3, 4, 5. Okay. Okay. And then here same thing. Something like this, okay guys? Okay, and then it comes the same thing right here. So what will happen here? This is the pulse width modulation. It will come and divide each pulse into pulses with different distances. So what will happen now to the current? We explained the current, guys, here. It goes charging, right? Then when I open, because I will here, this is on, right? This is what? This is when it's open, right? I have one cycle. This is on, this is off. This is when I switch on 1 and 4, and this one here when I open them. Okay? So what will happen when I open them? Let's see here. So I'm gonna look at the first one. I'm gonna use the red. Let's look at 1 and 4 when the current passes through the IGBT. When the current passes through the IGBT, what will happen actually? The current will increase or decrease? The current will increase or decrease? When the current passes through the increase, right?
Yes.
So I will have it like this, increasing. Okay? And then, when I open 1 and 2, 1 and 4, what will happen?
Decrease.
Because this will release, right?
Yes.
So it will decrease.
Yes.
It will decrease. Okay? The next one, same one, right? Next one.
Increase.
Increase, decrease, right? Increase, decrease, increase, decrease, increase, decrease, increase. Okay, guys? You see that? Now it's the opposite, right? Decrease. Okay? This is decrease, increase, decrease, increase, decrease, increase, decrease, increase, and decrease. And then you do the same thing right there. Okay? You're gonna do but the opposite now here because it's in the negative, right? So when it's on here, so it will increase in the negative, right? And then decrease, increase in the negative, 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 then decrease, and so on, right? Opposite? Okay, this is, so this one increasing here, right? And this is decreasing, right? Increase. decreasing. Wow. Is this one better than that?
Yes.
Can I make this better right here? How many I have here? 9, right? So 9 and 9, that's 18, right? Here was just 2, right? Ooh. Can I make this better? The current sinusoidal, how? What should I do?
Put more.
Huh? Put more? Yeah, it's okay. I'm gonna bring my textbook. Stay there. I'm gonna show you something. Okay, in the textbook, guys, if you go to, can you put this down, please? Look here, guys. Guys, look at this here. Okay. Look at this. This is 10, and this is 41. Okay. This is 10 and 41, guys. You see here? This is 10 and this is 41. Do you see a difference?
Big difference.
Big difference, right?
Yes.
Which one is smoother?
The first one.
The 10 or the 41?
41.
This is 41, the top. 41, right?
Yes.
Smoother. Means if I increase the frequency of my pulse width modulation, I will have what? I will have a smoother, right? So with this way I solve the current issue. Okay? I solve the current issue. Can I make it more smoother? Which is sinusoidal wave? Yes. Remember I told you in the beginning of the semester when we do rectifier, I told you inductance. When we rectify, if you use a huge inductance, you get straight DC, right? You get straight DC. Same thing right here. If I increase my inductance, I will get what? Smoother what? What do you mean by smoother? No, I will get pure sinusoidal wave, the opposite. In the inverter, if I use huge inductance, I get pure sinusoidal wave. Pure sinusoidal wave, right? In rectifier, if I use huge inductance, then I get straight DC, right? Okay, so this is what you need to know about inverter, single phase inverter, and then you can go back and listen to other lectures and also go back to your textbook. But I think this is as introduction for single phase inverter. You can follow me to the station there, okay? From there, you can come from there. We can guys come to the station right here. Okay, this is IGBT right here, and those we have 4 IGBTs, and this is our load. Okay, and this is a connection, basic connection. Make sure you do the connection. We close the switch, and we apply this time function generator, guys. Okay, we apply function generator, and we choose the pulse width modulation right here. Pulse width modulation, and we apply sinusoidal wave in the function generator, and we have pulse width modulation. So you can come here and see. You can see the pulse width modulation changing here, and also the sinusoidal wave right here. I can play with my frequency right here. Okay, see here the frequency with the pulse width modulation. See how the pulse width modulation is changing. I can increase. Okay, I can increase more. Okay. Okay, so that's the pulse width modulation. So by using if I decrease the frequency, which is for the sinusoidal wave, you see here, that's why with decreasing and if I decreasing it will be moving so slow. That's the sinusoidal wave. Increase, that's better. If I increase it more, then there will be a lot. So this is the best frequency for us, and this is the experiment for inverter, for single phase inverter. Okay, thank you.